In section 14.2, we introduce the concepts of limits and continuity to functions of two variables. So first, we're going to take a look at how to show that a limit does not exist for functions of two variables. So if you remember back to Calc 1, one way to show that a limit doesn't exist is to calculate the left-handed limit and right-handed limit and show that the two values are different. So this typically occurs when a single variable function has a jump discontinuity. So let me quickly draw such a situation in the corner here, right? So imagine you have the xy plane, and at some point, some x value, we're trying to look at the limit and say your function has some kind of jump discontinuity here, so like something like this. And so you can see for such a type of function, if you approach the x value from the left and from the right, they approach different y values. And so this is what I mean by the left-handed limit and right-handed limit have different values, right? So the y value is the value of the limit. And so here they have different values. And so the limit doesn't exist. So we can do something similar for functions of two variables, except the situation is more complicated because again here because the x is the only variable here, right? So when you approach a specific x value, you can only approach in two directions, so from the left and from the right. However, now because both x and y are input variables, so when we approach a point in the plane, it's possible to approach in infinitely many different ways, right? So when we approach, we have to take a path along some curve and approaching the specific points that we're looking at, right? So in this case, it's denoted a comma b. So when you take the limit approaching a b, you have to imagine taking all different kinds of paths to approach the point. And again, there's infinitely many different ways to do that, right? So you can approach along a straight line, you can approach on a slight curve like this, or you can approach along a more oscillating path like this, right? So every possible path to approaching the specific point needs to be considered. So because there's infinitely many ways to do that, it makes the situation more complicated. So how can we show a limit doesn't exist, right? So we only need two particular paths. So if we're able to find two particular paths, P1 and P2, such that when you approach the point that you're interested in, and the limit along one of the paths has a different value from the limit along another path, then the limit doesn't exist, right? So basically, we just need to find two paths along which the calculation of the limit gives you different values, and then we can say that the limit doesn't exist. So you can sort of have a situation where, say, the limit along this path is the same as the limit along this path, as these. So to say along all the pink paths, the value of the limit is one value, and say if I take this blue curve here and the limit happens to be a different value, then I can say that the limit doesn't exist. But again, the situation, it can be somewhat complicated, right? So first, to apply this method, we have to suspect that the limit doesn't exist, which isn't always easy to tell just by looking at the function, and second, trying to find those two paths which have different values can also be sometimes difficult. Okay, so with that in mind, we can sort of do it somewhat systematically by first starting with easy paths and slowly taking more complicated paths until we find the ones that we want. So sort of a procedure is listed here, right? So we can try some typical paths, sort of starting from easier paths and slowly getting more complicated. 1 and 2 are essentially these straight line paths, so like vertical paths and horizontal paths. So 1, you fix y. So here we're approaching the point a comma b, right? So you fix the y value to be equal to b, so you just plug it into the function, and then the resulting function will only be in terms of x, and so we have a single variable limit to calculate, and so we just calculate that single variable limit. So that's the first limit, and then similarly we can fix x equals a, and then the resulting function will only be in terms of y, and so we can calculate that single variable limit. So these are the horizontal and vertical paths. And then you don't have to approach on these specific lines, right? So again, you can take any path. So the remaining steps are sort of describing the situation where the limit is going to the origin, because most of the probably all the limits that we'll see in this course are going to the origin, because again, it's these two variable limits are somewhat complicated. So we don't want to take things to be too difficult. So if you're approaching the origin, what you can do is approach on a slanted line. So say y equals x, right? So imagine you approach on the diagonal. So if you take that path, so you just plug in y equals x into the function, then the resulting function will only be in terms of x, and then again, that's just a single variable limit that you can calculate. And then similarly, steps 4, 5, and 6 slowly take more complicated paths. So instead of y equals x, you can take lines with different slopes and then try to calculate those limits. You can also take a path following a parabola, so y equals x squared, and you calculate that limit. And you can also take y to be different powers of x, or x to be different powers of y. Okay, so again, what we're trying to do here is to show that a limit doesn't exist by trying to find two particular paths that have different values. Okay, so finally, let's try to apply this method to example 1. The limit, so here again, to keep things simple, we're approaching the origin, and my function is xy over x squared plus y squared. Right, so I'm going to start from the top of the list here and try to calculate these limits along these particular paths. Right, so here again we're approaching the origin. So in steps 1 and 2, my b and a are both 0. Right, so a comma b is just the origin. Okay, so if I apply the first path here, right, so b is equal to 0, right, so we set y is equal to 0. So let me scroll a little bit so I have more space, right? So we're setting y equals 0 into the limit. So if I just plug in directly into the function, what does it look like? It looks like this. Right, and so you see, once you set y equals 0, the resulting function only now contains x as a variable, right? So this now is just a single variable limit as x goes to 0. that we can calculate. Okay, so now how do I calculate this? So as always, you simplify this expression as much as possible before finally calculating the limit at the end, right? So in the numerator here, 0 times anything is equal to 0, and in the denominator you have x squared plus 0, which is just x squared, right? And then again we're still simplifying, so 0 divided by anything is always just equal to 0. And then now it's simplified as much as possible, so now we can calculate the limit, but this is just the limit of a constant, which is always just the value of the constant. So this limit is equal to 0. Okay, so along the first path, I get that the value of the limit is equal to 0. So that's sort of the idea with these calculations here. So the other paths are similar, right? So in 2, now I set x equals a, but a again in this example is just 0. So I set x equals 0, plug it into the function, so you get 0 times y over 0 squared plus y squared. So now this limit only contains y, so it's a single variable limit. And again, before calculating the limit, you simplify the function as much as possible, right? So 0 times y is just 0. The denominator is y squared. 0 divided by anything is just 0. So this is just a limit of a constant, which is the value of that constant, which is 0 in this case. Okay, so far the value of the limit along these two paths has the same value. So we can't say that the limit doesn't exist yet. Okay, so let's continue. Step 3 says now I try y equals x. So we set y equals x. So plugging it in, what does it look like? X times x over x squared plus x squared. Right, so you see now there's only the variable x, so this is a single variable limit. Now we simplify. So what do we have? X times x is x squared plus x is 2x squared. Right, so always simplify as much as possible before calculating the limit at the very end. Right, so x squared over x squared, that cancels out. Right, so this cancels this. So we're just left with 1/2. And again, the limit of a constant is just that constant, which is in this case 1/2. And so now you see along the path y equals x, I have a different value than previously. And so, this shows that the limit doesn't exist. So the value of the limit along the last path is different. So the limit doesn't exist. Okay, so that's the basic idea. Again, I mean, here originally looking at the function, it's not obvious at all that the limit isn't going to exist. So basically we just try to follow this procedure and sort of try to look at which values we're getting for the limit. And in this case, we see that we have different values.